In this video, we take a look at hydrostatic force and pressure. So everyone is probably familiar with the idea that if you're in the water, in a swimming pool or a lake or the ocean or something, and you dive down in the water deeper and deeper, there is more force being exerted on you. And that's the concept of hydrostatic force and pressure. So hydrostatic force is defined as density times the cross-sectional area times the depth. And we're using S for the depth now, rather than D for distance, but S is the depth from the surface. So in other words, the density of water, rho, which is a constant, so rho is always going to be a constant, the density of water, the depth of the water, and then the cross-sectional area of the surface. So you can see that the depth makes a big difference. As you increase the depth, you're going to increase the force. Now this is hydrostatic force. Hydrostatic pressure, we simply take the force and divide it by area. So hydrostatic pressure is simply the density times the depth. So that's basically what you're feeling. When you dive down in water, the pressure that you feel on your ears in particular is a function of the density of water, which is a constant, times the depth. So the only thing changing is the depth. So as the depth increases, that pressure that you feel exerted on you is also increasing. But I don't think we actually have any problems. We're looking for pressure. Most of the time, we're going to be looking for hydrostatic force. So if the surface, if we have a circular plate, like it shows us in this picture, and that circular plate is lying horizontally, and we consider there to be really no depth, it's two-dimensional, then the force, which again is the density times the cross-sectional area times the depth, then this is also going to be a constant. Okay, so at any particular depth, everything here is a constant. The density is a constant. The cross-sectional area is a constant only because it's all at the exact same depth, and the area is the same, and this is the same. So it's not too difficult to figure out what the force would be if it was horizontal. But what happens if that plate is standing up vertically in the water? Well, now that we have the plate vertically like this, then every point on that circular plate has a different amount of force being exerted on it because it's at a different depth. The depth is changing. So we're going to do a real quick development. We're breaking this circular plate down into a bunch of little slabs or rectangles. And so down here, remember that force is, that we just got through explaining, force, F, is the density times the cross-sectional area times the depth. So how do we figure out the cross-sectional area? The cross-sectional area, if we're creating a little slab here, is going to be the width of that rectangle by the thickness of the rectangle. In other words, this is the area, the width times delta x. So the force being exerted on this plate is the density times the cross-sectional area times the depth, these three things. Now, we take and we sum up all of the various tiny little slabs, and we have ourselves a Riemann sum. Then we let the number of slabs approach infinity, and we have the limit as n approaches infinity of our Riemann sum, which gives us our integral. Now let's break this integral down. Okay, the integral from a to b. We have three elements in this integral. We have rho, which is the density, which is a constant. We have w of x. That's my width. That's all that is, width. Just think of it, it's the width of that little slab. And then S of x is depth. It's a depth function. But the depth is a function. The width is going to be a function. So you have two functions that you need to find. And so you have a problem-solving strategy that you can read if you do so choose to. And I am going to explain to you how I go about doing these problems. So, a water trough, 15 feet long, has ends shaped like isosceles triangles. That is a really bad drawing, by the way. It should be more like that, I think. So that would be a little bit better. With base of 8 feet and a height of 3 feet. Find the force on one end of the trough if the trough is full of water. So again, the first thing you always want to do is create a little bit of a sketch. The next thing I want to do, just like I talked about in the last set of video notes, is are you in US standard or are you in metric? So we are in the US standards because we're talking about feet. So therefore, density is 62.4. And so here's what the integral breaks down into. This integral back up here, okay, this one right here, breaks down into this. Okay, this is what you need to find. You need to know density. We're given that. You need to know your width function. You need to know the depth function. And then when you put those three things into the integral, your density is a constant, so it comes out in front. You need to know your bounds of integration. And then in the integrand, you are multiplying your width function times your depth function. And that's it. So that tells you what you need to find. Remember this, okay? Density, integral, width function, depth function. So how do we find the width function? Well, we're going to have to use similar triangles again. You see, that's a common problem-solving technique with a lot of these problems. And so, similar triangles, we know that this distance right here is 4. This distance right here is 3. So we can create a ratio. 4 is to 3. And so we want some radius in here. Let me do that in green. So some radius right here to this distance. And there's our similar triangles. All right. So this distance here I'm calling R. And so this distance here is going to be 3 minus x. Same reasoning as in the problem that we did in the last video. All right, so think about that one. Go back to that last video if you need to figure that one out. And so solving this for r, we have r is equal to 4 times 3 minus x over 3. Now, be careful. Okay? R is only half the width. The whole width is 2 times r. This is w. That's the width. So w is 2 times the radius. All right, so that's why I wrote that here. And so here's my radius. I multiply that by 2, and I get this. So I'm just multiplying the 4 by 2 to get 8 times 3 minus x over 3. Solving that for w, simplifying it, we get 8 minus 8/3 x. So there is my width function. Got that? Check. Got density? Check. What about my depth function? Well, the depth, once again, just like with the other problems that we were doing, if we let x equals 0 be at the top, okay, x equals 0 at the top, and so this distance here is a distance x. So this is x equals 3 down here, x equals 0 at the top. So any place in between is some distance x. So I probably have that written down here. Yep, I do. So my depth function is simply x. All right, once we've got all that, I've got my width function, I've got my depth function. Let's put it all together. So density, bounds of integration. Well, I didn't talk about the bounds of integration, but we're going from 0 to 3, from the top to the bottom. There is my width function. there is my depth function. Simplifying this, multiplying those by x, we get that. Finding the antiderivative, we get that. Evaluating the antiderivative at 3 and 0 and subtracting, we get a hydrostatic force of 748.8. All right, so let's real quickly go back to this. And I said, I'll let you think about it, but I'll just go back and explain it because I'm enjoying making these videos. So we were doing the similar triangles, and I said this was R, and so this distance here was 3 minus x, right? That's because this whole, go away, this whole distance from here to here is 3, and then this distance here is x, so you take the whole distance minus the x to get 3 minus x. So that's another common little trick that we use a lot. Next problem. A hemispherical plate with a diameter of 10 is submerged vertically 2 feet below the surface of the water. Express the hydrostatic force against one side of the plate as an integral and evaluate it using technology. The reason we're going to do this using technology is because we can't actually integrate it using the standard methods that we have. In the next chapter, again, we'll learn some other techniques for doing this. The important part here is to demonstrate that you know how to set up the integral properly. All right, so feet, we're in the US standard units. So density of water is 62.4. My basic formula structure is density times width times depth. So I need all of those things. I have density. I need a width function and a depth function. Well, the width function, again, the width is constantly changing. The width is this distance here, okay? And then as we go up, okay, the width is constantly changing. And so what we can do is we can use the formula of a circle. So if we want to find the y value, so here's the center of a circle. If we put a point out here, that's a point x, comma, y. And so this is a circle. And so we know that x squared plus y squared is equal to the radius squared, and the radius is 5, so radius squared is 25. So here's my basic equation of this circle. And so what we want to do is we want to find the y value for any particular x value. All right, and so just solve this for y. So y squared is 25 minus x squared, so y is equal to technically plus or minus, but we're going to disregard the minus square root of 25x squared. Just think about the positive root. All right, so that okay, so actually that is actually calculating. So I'm usually using x as the distance up, so I'm using this as y. Forgive me. This could seem a little confusing here now, because remember we're measuring x vertically now. Yeah, the x is vertical. So if this distance is a distance x, we got to use y as being the horizontal distance. So it's all kind of backwards, but you guys will get it. All right. So y is equal to the square root of 25 minus x squared. And so 2y is 2 times square root of 25 minus x squared. That is my width function. And then finally, my depth function is in terms of x. So again, I'm letting, whoops, didn't quite draw that correctly. Here's the top. From here, top is here to here is x, but we also have this distance of 2. So the distance that we're pumping is we're pumping up a distance of x plus an extra 2 feet. So there's my distance function. Now the bounds of integration is simply from x equals 0 to x equals 5. Okay, because we're only going this distance here. So putting it all together into this, we have density times the bounds from 0 to 5. There is my width function. There is my depth function. Now, there's no way we're going to be able to integrate that easily. Again, in the next chapter, chapter 3, we're going to learn some techniques where we can do this. But right now, just put that integral into Desmos. And when you put it into Desmos, you should put this into Desmos, just like that. Don't simplify it or do anything else. Just put it in there. You should end up with 10,100.88, which is 10,101 because it says round to the nearest whole number for some reason. So that's what you do. Okay, so lots of little pieces. But again, if you just go back to this basic format for these problems, density times width times depth. One more problem, and then we are done with this section. I think it's just one more, yeah. Let's see, I have not used violet. A triangular plate with a base of 4 meters and a height of 5 meters submerged vertically in water so that the tip is even with the surface. So the tip has to be even with the surface right here. And so we have a depth of 5, the base is 4. Express the hydrostatic force against one side of the plate as an integral and evaluate it using technology again. Actually, this one we can actually evaluate. We don't have to do it using technology, so I would suggest that you do that. So let's figure out the pieces. We know, oh, and this one, yeah, this is in meters. We're in the metric system. Metric. Glad I threw one of these in here. So remember, the only difference with the metric system is you need to include G, 9.8. So instead of just the density, it's the density times G, just like I explained in the work problems in the previous video. All right. Anytime you're in the metric system, the only difference is you're multiplying the density times G, 9.8 meters per second squared. So we have both of those are constants times the integral from A to B times my width function times my depth function. So they don't tell you here, but it is water. So, and I've told you before, and now you're hearing it again. I don't remember the units. Don't tell anybody I said that. But it's 1,000 times 9.8 meters per second squared. Meters per second. Something like that. So I'm terrible with units, by the way. I figure, okay, I'm math. I just care about the numbers part. But, you know, don't tell any of the math instructors I said that. So we end up with 9,800 from that. That's my constant. Now, my bounds of integration is we're looking from x equals 0 to x equals 5. So there's my bounds of integration. Well, what about my width function? Well, similar triangles again. Here's the third time or fourth time we use similar triangles. And so we get radius is 2/5 x. The width, so the radius is just this. The width is twice the radius. So the width is 4/5 x. 2 times 2/5 is 4/5 x. And the depth is just x. So we have the width function times the depth function. You can multiply those together. You get 4/5 x squared. You can integrate that. You get 4/5 x cubed divided by 3, which is 4/15 x cubed. Evaluate that from 5 to 0, multiply by 9,800, and voila, you get that. Stick it in Desmos just to check it out and make sure that they are in agreement. All right, well, this is a long chapter, section 2.5, so we're actually doing it over 2 different days. One, like I said at the end of the last video, if I was teaching this in class, I would be teaching it over 2 different class periods. So I'm doing it the same way online, giving you more time to work with these problems. I've broken down in weeks 2.5a or 2.5 part 1, 2.5 part 2. The videos and everything are exactly the same. It's just that I just replicated it all into the next week to know that you still have more time to continue working on it. All right, we'll see you in section 2.6 in a little while. Bye-bye.